Hi everyone, welcome to my video. So we're going to solve a question from Oxford MAT paper 2019. Question is about a right angled triangle and it connects trigonometry with geometric progression. So if you like to pause the video, read the question and try solving it yourself first, then we could go over it together. Right, okay, so I could think of a couple of different approaches to this question, solving it in a couple of different ways. So the first thing is that notice we're given that this is a right angled triangle, and another key information is that the sides are positive numbers and it is geometric progression. So in other words, we have AR squared. These are the lengths of the triangle, right? So what we can deduce from a given information that the side lengths are positive, since A is one of the lengths of the sides, A has to be greater than 0. And what is hidden here slightly is this implies R must be positive as well. Now, why is that? Because if you think about it, since A is positive, if R is negative, this would be negative. And since AR is one of the lengths of the triangle, the side length, that means it can't happen, so R has to be positive, right? And of course, the next challenge now is to consider whether R is less than 1, or sorry, if R is between 0 and 1, or if R is greater than 1. Why is that important? Well, when we're constructing the triangle, we have to consider whether that will make any changes. So let's call this ABC, and the question says tan BAC, so we're interested in that angle. Now, if R is greater than 1, that means this will have to be AR squared, yeah? And the other two will be AR and A, let's say. But if R is between 0 and 1, that means this will have to be A. In other words, this would be AR squared and AR, or vice versa, you know. Yeah, okay, so there are a few things to consider here. But if we simply look at tan theta, so tan theta will equal to opposite, looking at the red writing over A, that gives us R, or tan theta is equal to again, this time looking at the green, AR divided by R squared, that's 1 over R. If you construct the same triangle, for, R is greater than 1, or R is between 0 and 1, or the swap size of length of the sides, you will always get tan theta to be R, or 1 over R. So this is the only two case that we need to consider, okay? Now, how do we do that? Well, doesn't really matter which one we use. Let's use the red writing, so AR squared. This is Pythagoras. C squared is equal to A squared plus B squared. I'm using these three here. Yeah. Now, if you were to use the green colored lengths, it wouldn't, yes, the Pythagoras' theorem would give you something slightly different, but because now we are aware of tan is also equal to 1 over R, we can simply take care of that as we're solving this, so we don't have to write two Pythagoras' theorem, two equations using Pythagoras' theorem. So if we expand this, we have A squared R to the 4 is equal to A squared R squared plus A squared. Now, A is not equal to 0, that means A squared is not equal to 0. So let's divide by A squared. R to the 4 is equal to R squared plus 1. That implies R to the 4 minus R squared minus 1 is 0. Now, let's go back to our equations. What is R equal to? Well, R is equal to tan theta, isn't it? Or let me write here. So we have R is equal to tan theta, or 1 over R is equal to tan theta, okay? So let's sub R to be tan theta, let T be tan theta, so we have T to the 4 minus T squared minus 1 is 0. let y is equal to t squared, so we have y squared minus y minus 1 is equal to 0. That implies y minus a half. Completing the squared, we get that if you complete the square. Now I'm going to take the square root of it, but notice since y is equal to t squared, y has to be a positive number. So I'm just going to say y minus a half is equal to not plus minus, but just plus root 5 over 2. So that implies y is equal to 1 plus root 5 over 2, which is equal to tan squared from the definition of y. So t is equal to square root of 1 plus root 5 over 2. Now notice I didn't say plus minus here again, because we know t is equal to r. So tan theta is equal to r, and we argued that r must be positive, if you remember in the beginning, so r is positive. Therefore, we can just ignore the minus sign. Now, if we used the other possibility where tan theta is 1 over r rather than r, so if I continue from here, so now if tan theta is equal to 1 over r, that implies r is equal to 1 over t. And if I sub that in, so if I sub that in to here, I should have drawn arrow from there, sorry. Yeah. So what we have is we have r to the 4. So in other words, this will be 1 over t to the 4 minus 1 over t squared minus 1 is equal to 0, right? Now let y is equal to 1 over t squared. That means y squared is 1 over t to the 4. So we have y squared minus y minus 1 is equal to 0, right? And if you notice that these two polynomials are identical, so that's just right. But this time, instead of t is equal to that, we will have 1 over t is equal to that, because 1 plus root 5 over 2. And the reason for that is because this time y is equal to 1 over t, yeah? But now that means t is equal to 2 over 1 plus root 5 square rooted. Now let's focus on the term in the square root sign. Let's rationalize the denominator. Root 5 over 1 minus root 5, that's equal to 2 minus 2 root 5 divided by 1 minus 5, that's equal to 2 minus 2 root 5 divided by minus 4. And we multiply this by minus 1 over minus 1, so we will have 2 root 5 minus 2 over 4, that's equal to root 5 minus 1 over 2 if we cancel 2's, right? So in other words, t will equal to square root of root 5 minus 1 over 2. So in other words, that becomes that, okay? And if you go back to the answers, the correct answer is C, because this is precisely what we have got, right? Okay, excellent. Well, I hope you found it interesting and inspiring. And thank you for joining, and I look forward to seeing you in my future videos. Thank you.